Alright, let's go. Number 8. Mercury. Mercury rotates so slowly that a single day lasts 59 Earth days. This means if you landed on the surface at dawn, you'd have weeks to watch the sun rise before it killed you. Standing on Mercury's sunlit side, wearing nothing but a pressure suit, the temperature would reach 430 degrees Celsius within your first hour. On March 18, 2011, NASA's Messenger spacecraft entered orbit around Mercury, becoming the first probe to orbit the solar system's innermost planet. Its instruments confirmed what scientists had long suspected. Mercury is a world of brutal extremes. Scientists expected Mercury to be hot, but the measurements revealed conditions more severe than theoretical models predicted. The sunlit side reaches temperatures high enough to melt lead and zinc, while the dark side plunges to negative 180 degrees Celsius. The planet essentially has no atmosphere. Its atmospheric pressure is 1/trillionth of Earth's, offering no protection from solar radiation that bombards the surface at nearly 7 times the intensity of what we experience. With no magnetic field to deflect the solar wind, the surface is constantly scoured by charged particles streaming from the sun. What makes Mercury particularly unsettling is its contradictory nature. Despite surface temperatures that could vaporize most substances, NASA's Messenger mission discovered water ice in permanently shadowed craters near the poles in 2012. These ice deposits exist just kilometers from regions hot enough to melt metal, suggesting thermal dynamics far more complex than models can fully explain. Death on Mercury would be straightforward but inescapable. The thermal radiation would penetrate your suit within minutes, cooking you from the outside in. Your skin would blister and char as your body temperature climbed, past the point where proteins denature and cellular structures collapse. There would be nowhere to run. Mercury's dark side offers only the opposite extreme, cold enough to freeze carbon dioxide solid. You'd have weeks to watch the sunrise that would kill you, a slow-motion execution by the nearest star. How many other worlds in the universe offer such a prolonged view of approaching death? Number 7. Uranus. On January 24th, 1986, Voyager 2 made its closest approach to Uranus, humanity's only visit to this tilted ice giant, lying nearly 3 billion kilometers from Earth. The spacecraft's instruments detected something unexpected that defied orbital mechanics and planetary science. Uranus has the coldest planetary atmosphere in the solar system, even though it orbits closer to the sun than Neptune. At negative 224 degrees Celsius, Uranus's cloud tops are colder than any other planet we've observed. If you fell into Uranus, you'd freeze before you were crushed. Planetary scientists expected temperature to correlate with distance from the sun. Neptune being farther out should logically be colder, but Voyager 2's measurements revealed an anomaly that challenges our understanding of planetary heat dynamics. Most gas giants radiate more heat than they receive from the sun, leftover energy from their formation still bleeding into space. Uranus radiates almost nothing. Its internal heat appears to have been shut off, leaving only the faint warmth from distant sunlight to combat the cosmic cold. The most compelling theory suggests a massive impact billions of years ago knocked Uranus on its side, giving it an axial tilt of 98 degrees. This catastrophic collision may have disrupted the convection currents that transport heat from the planet's interior to its surface, essentially turning off its internal furnace. But nearly 40 years after Voyager 2's flyby, scientists still cannot fully explain why this planet remains so extraordinarily cold. Descending into Uranus would be a gradual transition from horror to horror. You'd fall through an atmosphere of hydrogen, helium, and methane, watching the faint blue light fade to absolute darkness. Wind speeds of 900 kilometers per hour would buffet you violently. The temperature would plummet as you descended, your body heat radiating away into the surrounding gas. Long before the pressure could crush you, the cold would penetrate your suit. Your extremities would freeze first, ice crystals forming in your tissues. Your core temperature would drop, triggering violent shivering that would gradually weaken as hypothermia set in. As you descended through layers of gradually increasing pressure, your body would freeze solid long before the crushing depth could destroy it. A cosmic deep freeze that would preserve your final expression for eternity in the darkness. What other secrets does this sideways world hold in its frozen depths? Number 6. Neptune. In August 1989, Voyager 2 captured images of Neptune's Great Dark Spot, a storm system the size of Earth with winds reaching 1,300 miles per hour, the fastest in the solar system. These supersonic winds would tear you apart before the crushing pressure deep below could. The spacecraft's encounter with Neptune, the most distant planet in our solar system at 4.5 billion kilometers from the sun, revealed a world of incomprehensible violence. Neptune kills you with violence first, then pressure. Scientists studying Neptune faced a fundamental puzzle. The planet receives only 1/900th the solar energy that Earth does, barely a trickle trickle of warmth from the distant sun. According to atmospheric models, this should produce relatively calm weather, gentle winds driven by minimal temperature differentials. Instead, Voyager 2 observed atmospheric chaos. Winds screamed across the planet at 2,100 kilometers per hour, faster than the speed of sound in Earth's atmosphere, faster even than Jupiter's winds despite Jupiter receiving 25 times more solar energy. What makes Neptune's winds so baffling is their energy source. The planet radiates 2.6 times more energy than it receives from the sun, suggesting internal heat drives the weather systems. But the physics don't fully explain how internal heat alone could generate such extreme wind speeds. Something about Neptune's atmospheric composition, 80% hydrogen, 19% helium, 1.5% methane, creates dynamics that surpass our current understanding of planetary meteorology. Death on Neptune would be violent and multifaceted. As you entered the upper atmosphere, the supersonic winds would hit you like a cosmic blender. The shear forces would be devastating, tearing at your suit, then your body. The temperature of negative 214 degrees Celsius would freeze exposed flesh instantly. If somehow you survived the wind shear, you'd continue falling into increasing pressure. Neptune has no solid surface, just a gradual transition to liquid and ice under pressures that reach millions of atmospheres at depth. The fastest winds in the solar system would shred your body in seconds, but Neptune's real horror lies deeper, where pressure creates a layer of liquid diamond rain, and your atoms would be compressed into unrecognizable configurations. Could any form of life evolve in such extremes, or does Neptune represent an absolute boundary for biological possibility? Number 5. Mars. On July 20th, 1976, Viking 1 became the first spacecraft to successfully land on Mars and transmit from the surface, touching down in the region called Christ Planitia after a nearly year-long journey from Earth. Its instruments measured atmospheric pressure at just 600 pascals, 0.6% of Earth's atmospheric pressure. At that pressure, discovered by the Viking mission's meteorology instruments, your blood would boil at body temperature. Mars doesn't suffocate you. It makes your bodily fluids boil while you're still conscious. Scientists had known Mars possessed a thin atmosphere since telescopic observations in the 19th century, but the Viking landers provided the first direct measurements of just how tenuous that atmosphere truly was. On Earth, water boils at 100 degrees Celsius at sea level because that's the temperature at which water vapor pressure exceeds atmospheric pressure. But the boiling point of water drops as atmospheric pressure decreases. On Mars, with pressure at only 600 pascals, water boils at 10 degrees Celsius, well below human body temperature of 37 degrees. This creates a phenomenon known as ebulism, where bodily fluids begin to vaporize. The physics of low-pressure exposure are well understood from high-altitude aviation accidents and chamber testing. At the Armstrong limit, around 63,000 feet on Earth, atmospheric pressure drops low enough that water boils at body temperature. Mars exists far below this threshold. NASA's MAVEN mission, launched in 2013, revealed that Mars loses about 100 grams of atmosphere to space every second, stripped away by solar wind because the planet's magnetic field died billions of years ago. Your death on Mars would be uniquely horrifying because of the sequence of events in your consciousness throughout. Within seconds of exposure, the moisture on your tongue and in your eyes would begin to boil. You wouldn't explode. Your skin and circulatory system would hold you together, but you'd feel the dissolved gases in your blood forming bubbles like the bends that afflict divers who surface too quickly. These bubbles would start at your extremities as pressure causes dissolved nitrogen and oxygen to come out of solution. The pain would be excruciating as bubbles formed in your joints and tissues. Your blood wouldn't boil instantly. It would start at your extremities as pressure causes dissolved gases to form bubbles, creating excruciating pain as you remained conscious for perhaps 15 seconds, long enough to understand exactly what was happening to your body. Does Mars remember when it had a thick atmosphere and magnetic field? Or has it been a frozen desert for so long that this is its natural state? Number 4. Saturn. On September 15th, 2017, the Cassini spacecraft completed its 20-year mission by diving into Saturn's atmosphere, transmitting data until the crushing pressure destroyed it approximately 1,900 kilometers below the cloud tops. The spacecraft's final moments, carefully planned by NASA engineers to prevent biological contamination of Saturn's potentially habitable moons, revealed precise measurements of atmospheric density and composition at depths no human will likely reach for decades. Based on those final transmissions, we know exactly how long you'd remain conscious while falling into Saturn. Approximately 22 minutes. Saturn, like Jupiter, has no solid surface to land on. The planet is a gas giant whose atmosphere transitions gradually to liquid metallic hydrogen under crushing pressure and extreme heat. Scientists expected this transition to be relatively uniform, but Cassini's instruments detected unexpected molecular complexity in the upper atmosphere, organic compounds and strange chemical interactions that suggest Saturn's interior is more dynamic than models predicted. The planet's famous golden cloud clouds, composed of ammonia ice crystals and hydrocarbons, give way to layers of increasing density where hydrogen and helium are compressed into exotic states of matter. What makes falling into Saturn particularly terrifying is the timescale involved. You wouldn't die instantly. You'd fall for 22 to 30 minutes, depending on your mass and cross-sectional area, experiencing every stage of increasing pressure and temperature. The planet's winds would batter you at speeds exceeding 1,800 kilometers per hour at the equator. As you descended, the pressure would increase exponentially. Your ears would pop, then ache, then rupture. The temperature would rise from negative 140 degrees Celsius at the cloud tops to thousands of degrees deeper down. Cassini's final transmission came from a depth where pressure reached multiple atmospheres and temperature exceeded 1,500 Celsius. The spacecraft simply stopped transmitting, presumably crushed and vaporized by conditions beyond its engineering tolerances. For a human body, the critical point would come much earlier. At around 5 atmospheres of pressure, equivalent to 50 meters underwater, your lungs would struggle to expand. At 10 atmospheres, your rib cage would begin to compress. At 20 atmospheres, your ribs would crack and collapse inward. You'd fall for nearly half an hour watching the golden clouds turn to darkness, feeling the pressure increase with each kilometer, until somewhere in that crushing void, your ribs would collapse inward and your consciousness would finally cease, miles from anything solid. What lies at Saturn's core, and could anything survive in those unimaginable conditions where pressure transforms hydrogen into metal? Number 3. Jupiter. On December 7th, 1995, the Galileo probe entered Jupiter's atmosphere at 48 kilometers per second, the fastest atmospheric entry ever recorded, over 107,000 miles per hour. The probe, designed and built over 15 years by engineers who pushed the limits of material science, transmitted data for 57 minutes and 36 seconds as it descended 156 kilometers before being crushed and vaporized by Jupiter's atmosphere. If you fell into Jupiter, you'd remain conscious for most of that 57-minute descent, experiencing pressure increases that would compress your body to a fraction of its original size before finally killing you. The Galileo mission revealed Jupiter to be far more complex and hostile than scientists anticipated. The probe encountered winds of 650 kilometers per hour, massive electrical discharges, and atmospheric chemistry unlike anything on Earth. It measured temperature and pressure at depths no spacecraft had reached before, transmitting data until conditions exceeded its tolerance. At its final transmission, the probe had reached 23 Earth atmospheres of pressure and temperatures of 153 degrees Celsius. Engineers had designed the probe to survive deeper, making its sudden silence mysterious. Something in Jupiter's atmosphere crushed it faster than predicted. What makes Jupiter particularly deadly is its intense radiation environment, discovered by the Pioneer missions in the 1970s. The planet's magnetic field is 20,000 times stronger than Earth's, creating radiation belts that would deliver a lethal dose within minutes. Long before you reach the crushing depths, you'd be absorbing radiation that would begin destroying your cells. Jupiter's gravity, at 2.5 times Earth's, would make you feel as if your body weight had suddenly increased. A 100-pound person would feel like they weighed 250 pounds. The death sequence on Jupiter would unfold in stages, each more agonizing than the last. First, the radiation would begin its invisible work, damaging DNA and killing cells throughout your body. You'd develop radiation sickness within minutes, nausea, disorientation, cellular breakdown. As you fell deeper, the atmospheric entry would create tremendous heat from friction, though not as extreme as Galileo's supersonic plunge. The increasing gravity would make breathing difficult, your chest muscles straining against your own weight to expand your lungs. For nearly an hour, you'd fall through poisonous clouds while radiation sickness set in, your body compressed by increasing pressure, bones fracturing as you weigh more and more with each kilometer, until finally the pressure exceeds what your rib cage can withstand and your organs rupture internally. Jupiter doesn't just kill you, it kills you repeatedly, through multiple mechanisms acting simultaneously while you remain conscious for almost an hour of horror. Number 2. Venus. On March 1st, 1982, the Soviet Venera 13 lander touched down on Venus and survived for 127 minutes before its electronics failed, the longest any craft has functioned on the surface of Earth's so-called twin planet. Its instruments recorded conditions more hellish than any other world in the solar system: 475 degrees Celsius surface temperature, 92 Earth atmospheres of pressure, and clouds of sulfuric acid floating 45 to 70 kilometers above. The Venera program's remarkable achievement demonstrated that Soviet engineers had built something capable of withstanding hell itself, at least temporarily. Venus doesn't kill you quickly. It kills you in stages, each worse than the last. Venus and Earth are remarkably similar in size and composition. Both planets form from the same primordial material, both are rocky worlds with significant atmospheres, both orbit in the sun's habitable zone. Yet somewhere in their histories, Venus underwent a catastrophic transformation. The planet's atmosphere, 96% carbon dioxide dioxide created a runaway greenhouse effect that transformed the surface into an inferno. The atmospheric pressure at the surface equals the pressure 900 meters underwater on Earth, enough to crush a nuclear submarine. The temperature is hot enough to melt lead and zinc, maintained uniformly across the entire planet, whether you're on the day side or night side, equator or pole. What makes Venus scientifically terrifying is that we don't fully understand why this happened. Was Venus always hellish, or did it once have oceans like Earth before a greenhouse catastrophe boiled them away? Computer models can't definitively determine when the transformation occurred, or what triggered it. The Soviet Venera 7 achieved the first soft landing on another planet on December 15, 1970, surviving just 23 minutes. Each subsequent Venera mission lasted slightly longer as Soviet engineers refined their heat shields and cooling systems, learning to build machines that could temporarily survive conditions that would destroy any known life form. Death on Venus would combine 3 torture methods simultaneously over an extended period. First, the sulfuric acid clouds. Your suit would begin degrading immediately upon descent through the cloud layers, the acid eating through any exposed material. Once on the surface, the pressure would begin its work, 92 atmospheres, pressing on your body from all directions. Your rib cage would creak and compress. At the same time, the heat would penetrate your suit. Even the best insulation could only delay the inevitable. The temperature would begin cooking you from the outside in, your skin temperature rising degree by agonizing degree. Death would take perhaps 10 to 15 minutes. First, the acid would burn away your exposed skin. Then the pressure would crack your ribs. Finally, the heat would cook you from the outside in, your body temperature climbing degree by degree until your brain proteins denatured and consciousness mercifully ended, but not before you'd experienced every excruciating stage. Venus stands as a warning of what runaway climate change can do to an Earth-like world. A cautionary tale written in hellfire and crushing pressure. Number 1. The Sun. The Sun isn't a planet, but if we're discussing how you die on celestial bodies, no death would be more absolute. On February 9th, 2020, the Solar Orbiter spacecraft was launched to study the Sun closer than any previous mission, eventually reaching 42 million kilometers from its surface. That's still 670 times farther than you'd need to be for the radiation to kill you instantly. The Sun doesn't just kill you, it erases you from existence, atom by atom, converting matter back to energy in a process so fundamental it represents the ultimate form of death. The Sun's surface temperature of 5,500 degrees Celsius is merely the beginning. The real mystery, called the coronal heating problem, is why the Sun's corona, its outer atmosphere, reaches temperatures of 1 to 3 million degrees Celsius. This violates basic thermodynamics as we understand it. Heat should flow from hot to cold, yet the corona is hundreds of times hotter than the surface beneath it. The Parker Solar Probe, which made its closest approach on December 24, 2024, at just 6.9 million kilometers, has gathered unprecedented data, but scientists still cannot fully explain how the corona reaches such extreme temperatures. What makes death by the Sun uniquely absolute is the distance at which it occurs. Long before you approach the surface, at approximately 63,000 kilometers away, the radiation intensity would reach lethal levels instantly. The Sun bombards space with electromagnetic radiation across the entire spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. At 63,000 kilometers, the radiation flux is so intense that every molecule in your body would be simultaneously ionized. You wouldn't have time to feel pain. You wouldn't burn or vaporize through conventional heating. The radiation would strip electrons from your atoms, converting your body directly to plasma. The Parker Solar Probe's heat shield can withstand temperatures of 1,400 degrees Celsius, protecting its instruments as it samples the solar wind traveling at 400 to 800 kilometers per second. But no material known to science could protect a human at the distances where radiation becomes instantly lethal. The Sun's core, at 15 million degrees Celsius, fuses hydrogen into helium through nuclear fusion, releasing the energy that has powered our solar system for 4.6 billion years. Long before you reach the surface, at around 63,000 kilometers, the radiation would ionize every molecule in your body simultaneously. You wouldn't burn or vaporize, you'd be converted directly to plasma, your atoms stripped of electrons and scattered into the solar wind. There would be no remains, no ashes, no molecules that were ever you. The Sun doesn't kill you. It unmakes you from existence, returning your atoms to the cosmic furnace that created them 4.6 billion years ago. You wouldn't die on the Sun. You'd cease to have ever been anything but energy and light. If you want to see more videos like this, click the video on screen now and make sure to subscribe.